In 1942, the United States nearly lost World War II, not to German tanks or Japanese aircraft, but to a shortage of rubber. At the moment America entered the war, it possessed enormous advantages: industrial capacity, oil, steel, manpower. What it did not possess was a secure supply of one material that modern war could not function without: rubber. Within weeks of Pearl Harbor, Japanese forces controlled close to 90% of the world's natural rubber supply. The plantations of Southeast Asia, Malaysia, Indonesia, Indochina, had quietly been the foundation of America's military mobility for decades, and almost overnight, they were gone. The consequences were immediate, even if most people didn't realize it yet. Rubber was not a minor input. It was embedded in every moving system the US military relied on: tires, fuel hoses, seals, gaskets, electrical insulation, shock absorbers. A single bomber required hundreds of rubber components. A tank required thousands. A military truck needed 8 tires, and the Army planned to build hundreds of thousands of them. By early 1942, the United States had less than 6 months of rubber stockpiled. 6 months before trucks stopped moving. 6 months before aircraft were grounded. 6 months before tanks became immobile steel shells. Modern war does not fail when weapons are destroyed. It fails when movement collapses. And here was the deeper problem. The United States had no backup plan. Synthetic rubber existed, but only on paper and in laboratories. America had never produced it at industrial scale. Its chemical companies had ignored it. Natural rubber was cheaper, easier, imported by the shipload. Germany had tried to make synthetic rubber work for years and barely succeeded. For the United States to replace natural rubber, it would need to do something no country had ever done before: build an entirely new chemical industry from nothing, in the middle of a global war, before its existing supplies ran out. Engineers looked at the numbers and called the timeline unrealistic. Industrial planners said the materials weren't available. Executives privately admitted that even if everything went right, it would probably arrive too late. And yet, failure did not mean defeat in a single battle. It meant something quieter: factories slowing down, vehicles parked, operations postponed not because of enemy fire, but because nothing could move. This is the story of how close that collapse came, and how the United States tried to outrun it. Not by building perfect solutions, but by abandoning perfection altogether. Because in 1942, World War II wasn't decided by who had the most weapons. It was decided by whether an industrial system could keep moving, when one overlooked material suddenly became the most important resource on Earth. If you asked most people in 1941 what powered the American war machine, they would have pointed to steel, or oil, or factories. Very few would have said rubber. That was precisely the problem. Rubber was not dramatic. It didn't explode. It didn't fire back. It didn't dominate headlines or victory parades. It simply made everything else work. Every vehicle the US military relied on, tanks, trucks, jeeps, aircraft, landing craft, depended on rubber not as a luxury, but as a structural necessity. Without it, metal systems tore themselves apart. Engines overheated. Vibrations shattered components. Electrical systems shorted out. Rubber absorbed shock, sealed pressure, allowed motion without destruction. Modern war was not just a contest of firepower. It was a contest of continuous movement under stress. And rubber sat quietly at the center of that system. A single B-17 bomber required hundreds of rubber parts, not one or two, hundreds. Fuel hoses, hydraulic seals, electrical insulation, landing gear shock absorbers. A tank required thousands of individual rubber components, not just its tracks or road wheels, but the gaskets, seals, vibration dampeners, and flexible joints hidden deep inside its structure. Even something as mundane as a military truck depended on rubber in ways that multiplied quickly. Each truck required 8 tires. The US Army planned to build hundreds of thousands of trucks in 1942 alone, before accounting for jeeps, or artillery tractors, or aircraft ground equipment, or amphibious landing craft, or gas masks, or life rafts, or miles of insulated communication wire. Rubber wasn't a single line item, it was everywhere. And unlike steel or oil, Rubber was not something the United States could simply dig out of the ground or refine domestically. Natural rubber came almost entirely from Southeast Asia. For decades, American industry had built itself around that assumption. Plantations in Malaya, Indonesia, Indochina, ships arrived regularly. Prices were low. Supply was stable. There was no reason to imagine that flow would ever stop, which meant there was no reason, economically or politically, to invest in alternatives. Synthetic rubber existed in theory. It had been demonstrated in laboratories. Germany had experimented with it for years. But it was expensive, chemically complex, and most importantly, unnecessary. Why invest millions in a fragile industrial process when natural rubber could be imported cheaply and reliably? So American companies didn't. They focused on refining, not replacement, on efficiency, not resilience. By the time the United States entered the war, its entire rubber system rested on a single assumption, that Asia would always supply what America needed. That assumption collapsed almost immediately. When Japanese forces moved into Southeast Asia, they didn't just threaten shipping lanes or colonial territories. They seized the foundation of global rubber production. Within weeks, nearly all major rubber plantations were either under Japanese control or unreachable by Allied shipping. Submarine warfare made transport increasingly dangerous. Insurance rates skyrocketed. Deliveries slowed, then stopped. The flow that American industry had treated as permanent turned out to be fragile, and the numbers were brutal. By early 1942, the United States had less than 6 months of usable rubber stockpiled. Not 6 months to adapt, 6 months before the system began failing. Tires wore down faster than they could be replaced. Seals cracked. Hoses ruptured. Vehicles were cannibalized to keep others running. Factories slowed production, not because they lacked steel or labor, but because a missing rubber component brought entire assembly lines to a halt. This was not a future problem. It was already happening. Military planners began to realize that even if American factories could outproduce the Axis in tanks and aircraft, it would mean nothing if those machines couldn't be kept operational. A tank without replacement seals wasn't a weapon, it was a liability. An aircraft grounded for lack of rubber components didn't contribute to air superiority. It consumed resources without producing results. War, at this scale, was a system, and one small material threatened to collapse it. The most dangerous aspect of the crisis was not the shortage itself. It was that no one had built the system needed to replace rubber. Not the factories, not the workforce, not the supply chains, not the chemistry. There was no emergency stockpile of expertise waiting to be activated. There was only a ticking clock. And as 1942 began, it became clear that the United States was about to learn a hard lesson. Industrial strength meant nothing if it depended on a resource you did not control. Japan did not need to defeat the United States in a single decisive battle. It didn't need to destroy American factories. It didn't need to sink every ship or bomb every airfield. It only needed to interrupt one flow: rubber. For decades, the global rubber trade had followed a simple pattern. Plantations in Southeast Asia harvested latex. Ships carried it across oceans. Industrial nations turned it into tires, seals, hoses, and components. The system worked because it was stable. No one imagined it could disappear overnight. But in late 1941 and early 1942, it did. As Japanese forces advanced through Malaya, the Dutch East Indies, and Indochina, they didn't just capture territory. They captured the infrastructure of supply. Plantations, processing facilities, ports, shipping routes. Within weeks, nearly all major sources of natural rubber were either under Japanese control or effectively unreachable. This wasn't collateral damage, it was strategic leverage. Rubber wasn't just another commodity. It was the connective tissue of mechanized war. Japan understood that it didn't need to match American industrial output. It needed to deny America the materials that made that output usable. And the denial worked. Even when small amounts of rubber could be sourced from distant regions, the logistics were punishing. Longer shipping routes meant longer transit times. Japanese submarines targeted merchant vessels relentlessly. Insurance costs exploded. Convoys slowed. Every shipment became a gamble. The result was not an immediate collapse, but something more dangerous: uncertainty. Factories didn't know when the next delivery would arrive, or if it would arrive at all. Military planners couldn't rely on consistent resupply. Stockpiles were guarded, rationed, and quietly drained. Rubber became a controlled resource almost overnight. Civilian consumption was restricted. Speed limits were introduced to reduce tire wear. Drivers were urged to avoid unnecessary travel. These weren't symbolic gestures. They were signs of a system under strain. But rationing could only delay the inevitable. Rubber did not wear out evenly. It failed under stress. Military vehicles operated in extreme conditions: heat, dust, mud, salt water, vibration. Tires shredded, seals cracked, hoses ruptured. Every breakdown accelerated the crisis. To keep critical vehicles running, others were stripped for parts. Entire fleets were cannibalized. This created a cascade effect. Vehicles pulled from service reduced operational capacity. Reduced capacity increased stress on remaining equipment. Increased stress caused faster wear. The shortage fed itself, and there was no easy way out. Rubber could not be substituted with steel or aluminum. Metal parts rigid enough to replace rubber components transmitted shock and vibration, damaging engines and frames. Early experiments with alternative materials failed quickly. Some components worked briefly, then shattered. Others failed catastrophically. The material itself was the problem, and unlike oil or steel, rubber could not be stockpiled indefinitely. It aged. It degraded. Exposure to heat and oxygen weakened it. The reserves the United States had built were not a buffer, they were a countdown. By early 1942, American planners were forced to confront a reality they had avoided for decades. The global rubber system had been efficient, but it had not been resilient. It had optimized for cost, not survival. And now, under wartime pressure, that optimization was turning into a liability. What made the situation more dangerous was that the crisis was not visible to the public. There were no dramatic shortages in stores, no empty shelves, no single headline announcing disaster. The breakdown was happening deep inside factories, depots, and motor pools. A missing seal delayed an engine. A cracked hose grounded an aircraft. A shortage of tires sidelined trucks. Each incident seemed minor. Together, they threatened to paralyze the entire war effort. By the spring of 1942, the question was no longer whether rubber was important. It was whether the United States could keep fighting a mechanized war without access to the material that made mechanization possible. For the first time, American planners had to consider a grim possibility: that the war could be lost not because of enemy strength, but because a global supply chain had been severed, and no replacement existed. And that realization forced a choice: either accept a slow, silent collapse of mobility, or attempt something unprecedented, to rebuild, under fire, an entire industrial system that had never existed before. By the spring of 1942, the United States had finally named the problem: rubber. But naming the problem did not make it solvable. Because when planners looked closely at what replacing rubber actually required, the situation became worse, not better. The issue wasn't simply producing a substitute material. It was building an entire industrial ecosystem that did not exist. Synthetic rubber was not mined. It was not harvested. It was not refined from a single raw input. It was manufactured through a complex chain of chemical reactions, each one sensitive, unstable, and unforgiving at scale. And the United States had almost no experience doing that. Before the war, American companies had produced synthetic rubber in laboratory quantities, kilograms, not tons. Small experimental batches designed to test chemistry, not supply an army. In 1941, total U.S. synthetic rubber output amounted to a rounding error. It was measured in hundreds of tons, not hundreds of thousands. That wasn't a shortfall, it was an absence. Germany, by comparison, had been working on synthetic rubber since the 1920s. German chemists had pioneered polymer science. They had built dedicated facilities, they had trained specialists over decades, and even after all of that, Germany struggled to produce enough rubber for its own military needs. The factories were slow, their processes were expensive, their output barely kept pace with demand. If Germany, with 20 years of preparation, had difficulty making synthetic rubber work, what chance did the United States have? American chemical engineers understood this. They weren't pessimistic out of habit, they were pessimistic because they knew the constraints. Synthetic rubber required multiple critical inputs, not just one chemical, but an entire family of them. Each had to be produced in large quantities. Each required specialized equipment. Each depended on feedstocks that American refineries were not optimized to supply. Even if the chemistry could be solved, the engineering problem remained. Synthetic rubber plants were not simple factories. They were sprawling chemical complexes. Dozens of interconnected units, miles of piping, pressure vessels, heat exchangers, compressors. A single facility covered hundreds of acres. Under normal conditions, Designing and constructing a chemical plant of that scale took 3 to 5 years. Permits, fabrication, testing, commissioning. None of that fit the reality of 1942. The United States did not have 5 years. It didn't even have 2. And even if construction timelines could somehow be compressed, another problem loomed. People. Chemical plants did not run themselves. They required skilled operators, welders, pipe fitters, instrument technicians, safety engineers, specialists trained through years of experience. But wartime America was already draining its labor pool. Shipyards, aircraft factories, steel mills, every major industrial sector was competing for the same workers. Many skilled technicians were being drafted. Others were lured away by higher wages in military production. There was no reserve army of chemical workers waiting to be mobilized. Training new ones took time the rubber program didn't have. And then there was the most unforgiving constraint of all: scale. Chemistry that worked in a laboratory often failed when scaled up. Reactions behaved differently in large vessels. Heat built up faster. Impurities multiplied. Control became harder, not easier. A reaction stable in a glass flask could spiral out of control in a steel reactor the size of a house. Every experienced chemical engineer knew this, which is why many quietly concluded that even if a synthetic rubber process could be invented, it would collapse under industrial conditions. Too slow, too unstable, too sensitive. The final obstacle was coordination. Synthetic rubber was not one industry. It sat at the intersection of many. Oil companies controlled feedstocks. Chemical firms controlled reactors. Tire companies controlled formulations and performance requirements. These companies were not collaborators. They were competitors. They guarded patents, they protected trade secrets, they sued each other aggressively. In peacetime, this rivalry drove profits. In wartime, it threatened paralysis. No single company had the knowledge or capacity to build a complete synthetic rubber system alone, and no company had an incentive to share its most valuable information with rivals. From every angle, chemistry, engineering, labor, time, and coordination, the project looked doomed. Not because Americans lacked intelligence or resources, but because the problem violated the normal rules of industrial planning. Too complex, too rushed, too interdependent. Experts did not say it would be difficult. They said it would fail. And yet, by mid-1942, the United States had run out of alternatives. It could not wait for perfection. It could not wait for certainty. Either it attempted the impossible, or it accepted a slow collapse of military mobility. And that choice led to a decision that shocked nearly everyone involved. Instead of trying to build one perfect solution, the United States decided to break almost every rule it had ever followed, and build something imperfect, fast, and everywhere at once. By mid-1942, the United States had stopped asking whether the synthetic rubber program made sense. It was asking whether any rule was still worth following. In peacetime, industrial projects obeyed a familiar logic. You perfected the design. You minimized risk. You protected intellectual property. You built carefully, and you built slowly. None of that applied anymore. The rubber crisis wasn't a problem that could be solved elegantly. It was a problem that had to be outrun. So instead of trying to build the best synthetic rubber system, American planners made a radical choice. They decided to build the fastest one. The first rule they broke was competition. The U.S. rubber industry was dominated by fierce rivals: Goodyear, Firestone, Goodrich, U.S. Rubber. For decades, these companies had fought each other in court over patents, formulas, and manufacturing techniques. Their research departments were guarded like vaults. In normal times, that secrecy was valuable. In 1942, it was deadly. The government forced a choice: either share everything or watch the entire system fail. Under wartime authority, rival companies were compelled to pool their research, patents, and experimental data into a shared program. There would be no exclusive advantages, no proprietary shortcuts. Every company would have access to the same information. It was an extraordinary move. Executives objected. Lawyers protested. Chemists worried about losing years of work. But the alternative was worse. Without cooperation, no single firm could solve the entire problem. The second rule they broke was specialization. In peacetime, industries operated in neat lanes. Oil companies refined fuel. Chemical firms made chemicals. Tire companies made tires. The synthetic rubber program ignored those boundaries. Oil refineries were pulled into polymer chemistry. Chemical engineers were embedded with construction crews. Tire manufacturers influenced reactor design. The goal wasn't elegance, it was functionality. If a solution worked, even awkwardly, it was adopted. The third rule they broke was perfection. Traditional chemical engineering demanded precision, pure inputs, controlled environments, tight tolerances. But wartime America didn't have the luxury of purity. Raw materials were inconsistent, equipment varied, workers were inexperienced. Instead of rejecting imperfect conditions, engineers designed processes that tolerated them. Reactions were adjusted to handle impurities. Equipment was simplified so it could be built quickly. Quality standards were lowered to what was acceptable, not ideal. This horrified many specialists, but it kept the system moving. The fourth rule they broke was sequential construction. Normally, factories were built one at a time. You designed, you constructed, you tested, then you moved on to the next. That approach guaranteed reliability, and guaranteed failure under the rubber deadline. Instead, planners approved the construction of dozens of massive plants simultaneously. Before the chemistry was fully proven, before the workforce was trained, before supply chains were secure. It was a calculated gamble. If the chemistry failed, the losses would be enormous. But if it succeeded, the payoff would be immediate. This decision transformed the problem. The question was no longer whether one factory could work. It was whether enough of them could work well enough. To make this possible, engineers standardized everything: plant layouts, equipment designs, piping configurations. Each facility was a copy of the others. This allowed workers trained at one site to move easily to another. It allowed parts to be interchangeable. It allowed construction teams to repeat mistakes and then avoid them. Speed increased not because errors disappeared, but because they were learned from quickly. The fifth rule they broke was the idea that experts always knew best. Instead of deferring to academic chemists or senior engineers, the program elevated people who understood industrial reality. Engineers who had built refineries, managers who had run large plants under pressure, workers who knew how systems failed in practice. Theory mattered, but only if it survived contact with reality. This shift changed the tone of the entire project. Problems weren't treated as failures, they were treated as signals. If something overheated, it wasn't a disaster, it was feedback. If a reaction slowed, it wasn't a setback, it was data. The goal was not to eliminate problems, it was to solve them faster than time ran out. By late 1942, this rule-breaking approach had created something unprecedented. An industrial program that was chaotic, imperfect, and fragile, but alive. Plants rose across multiple states. Workers were trained as they built. Processes were adjusted in real time. Nothing about the system was optimized. Everything about it was urgent. And for the first time since Pearl Harbor, the rubber crisis stopped being a countdown to collapse. It became a race, not between nations, but between wear and replacement, between breakdown and repair, between how fast rubber was consumed. Whether the gamble would pay off was still unknown. But one thing was now clear. The United States was no longer waiting for a perfect solution. It was building one, even if it had to break every rule to do it. By late 1942, the synthetic rubber program had crossed a dangerous threshold. It was no longer theoretical. It was no longer a plan. Steel had been poured. Pipes had been welded. Reactors stood in place. Now the system had to run. And that was when reality pushed back. The first failures were immediate and relentless. Chemical processes that behaved perfectly on paper collapsed at scale. Reactions overheated. Pressures spiked. Entire batches of material were ruined in minutes. In a laboratory, temperature could be controlled with ice baths and careful timing. In an industrial reactor holding tens of thousands of gallons, heat behaved differently. The polymerization reaction that created synthetic rubber released enormous amounts of energy. If temperatures rose too quickly, the reaction didn't produce rubber. It produced solid, useless masses. Thousands of gallons of feedstock were destroyed. Valuable time vanished. Engineers adjusted cooling systems. They increased agitation. They slowed reactions. Sometimes it worked. Sometimes it didn't. The second failure came from speed. Even when reactions succeeded, they took too long. German synthetic rubber processes required extended reaction times. hours that American planners simply didn't have. Factories could not afford to run slow, careful batches. They needed continuous output. Engineers experimented under pressure. Catalyst concentrations were adjusted. Pressures were raised. Temperatures were fine-tuned. Every adjustment carried risk. Push too far, and reactions failed catastrophically. Move too cautiously, and production fell behind schedule. There was no safe zone. Then came contamination. In theory, synthetic rubber chemistry required oxygen-free environments. In practice, industrial plants leaked. Tiny amounts of air entered through valves, seals, and pipe joints. That oxygen poisoned catalysts instantly. Entire production runs stopped without warning. It was impossible to eliminate every leak in a system this large, so engineers changed the problem. Instead of trying to keep oxygen out, they added chemical scavengers that neutralized it on contact. The system became tolerant of imperfection. Not clean, but functional. While chemistry struggled, construction faced its own crises. Steel shortages were severe. The Navy had priority. Shipyards consumed massive quantities of metal. Weapons programs absorbed the rest. Rubber plants needed miles of piping, pressure vessels, and structural supports. The solution was improvisation. Engineers redesigned structures to use concrete instead of steel. Cooling towers were built from wood. Steel was salvaged from abandoned facilities and repurposed. Nothing was wasted. Labor shortages followed. Chemical plants required skilled welders, pipe fitters, electricians, and instrument technicians, workers who were in high demand everywhere. Many were drafted. Others left for higher-paying shipyard jobs. The response was radical. Training programs were compressed into weeks. High school graduates were taught welding, fitting, and basic instrumentation under crash courses. Experienced workers trained new recruits on the job. Quality standards shifted. Instead of demanding perfection, inspectors focused on functionality. Welds were tested quickly. If they held, work continued. Mistakes were inevitable, but delays were unacceptable. Equipment shortages created another bottleneck: compressors, heat exchangers, reaction vessels. Lead times stretched for months. Plants were completed before critical components arrived. Rather than wait, construction teams moved forward anyway. Structures were erected. Piping was installed. Electrical systems were prepared. When equipment finally arrived, specialized crews installed it in days. The system advanced in fragments, incomplete but moving. Yet the most severe pressure came from outside the plants. Rubber consumption did not pause. Military vehicles continued to wear out tires and seals. Operations expanded. New theaters of war opened. Every week of delay increased the gap between supply and demand. Plant operators worked under constant scrutiny. Government inspectors visited frequently, demanding increases. Military officers explained how shortages were already limiting operations overseas. The pressure was not abstract. Operators knew that failures at their plant could translate directly into grounded aircraft or stalled convoys. Plants ran continuously, 24 hours a day, 7 days a week. Maintenance crews worked during brief shutdowns. Repairs were performed under time pressure. Chemists monitored reactions around the clock. Adjustments were made mid-run. There was no room for stability. The system existed in a permanent state of correction. Slowly, almost imperceptibly, things began to change. Output increased. Not smoothly, not evenly, but measurably. Small improvements compounded. Cooling stabilized reactions. Adjusted catalysts shortened cycle times. Oxygen scavengers reduced failures. By late 1942, usable rubber began to leave the plants. The quantities were modest, but they proved something critical. The system worked. Not reliably, not cleanly, but it worked. And once that proof existed, the entire program shifted. Construction accelerated. Additional plants came online. Supply chains synchronized. The crisis was far from over. Rubber production was still below demand. Failures were still frequent. But the trajectory had changed. The system was no longer collapsing. It was learning, and learning faster than the clock was running out. By early 1943, something subtle but profound began to change. The synthetic rubber program was no longer asking a single question. Not, will this work? But, how fast can it scale? That shift mattered, because it meant the system had crossed the most dangerous threshold of all: uncertainty. For the first time since Pearl Harbor, American planners could see a path forward that didn't end in paralysis. Production numbers were still far from comfortable, but they were no longer hypothetical. Plants that had struggled for months were finally producing consistent output. Not perfect rubber, not optimized rubber, but rubber that worked. Tire manufacturers tested early batches cautiously. They expected failures. Instead, they found materials that met minimum performance standards. The rubber didn't last as long as natural rubber, it wasn't as uniform, but it could be used. And in wartime, usability mattered more than elegance. As confidence grew, production targets were raised. Plants increased operating pressure. Reaction times were shortened further. Maintenance schedules were tightened to reduce downtime. Every incremental gain mattered. At the same time, the supply chain surrounding the rubber plants began to synchronize. Butadiene production expanded rapidly. Refineries adapted processes to match local petroleum feedstocks. Styrene output increased as new catalytic reactors came online. For the first time, the entire chain, from oil well to finished rubber bale, began to flow continuously. This was not a single breakthrough moment. There was no announcement, no ceremony, no dramatic headline. The turning point revealed itself quietly, in spreadsheets and inventory reports. Monthly production numbers climbed, then climbed again. By mid-1943, synthetic rubber output reached levels that could no longer be dismissed as experimental. Warehouses that had once stood empty began to fill. Military procurement officers noticed the change first. Emergency requests slowed. Panic orders decreased. For months, the Rubber Reserve Program had operated in crisis mode, responding to shortages as they emerged. Now, for the first time, it could plan. That psychological shift was as important as the material itself. Plant managers stopped improvising hour to hour and began optimizing week to week. Engineers moved from survival fixes to efficiency improvements. Processes were standardized further. Training programs stabilized. Failure rates dropped. The system was still fragile, but it was no longer chaotic. By late 1943, production crossed a critical threshold. Synthetic rubber output approached, and then matched, military demand. For the first time since the crisis began, consumption no longer outpaced supply. The countdown ended. There was no dramatic moment when rubber suddenly became abundant, but the fear that had defined the program began to fade. Vehicles were no longer cannibalized at the same rate. Maintenance schedules normalized. Factories stopped hoarding components. Rubber was no longer the limiting factor. By early 1944, the implications became undeniable. The United States had not merely survived the rubber crisis, it had built something entirely new. An industrial system capable of producing hundreds of thousands of tons of synthetic rubber annually, independent of Asian plantations and global shipping lanes. The original goal had been survival. What emerged was dominance. The synthetic rubber plants continued to expand output even after demand stabilized. Stockpiles grew. For the first time, the United States possessed a rubber supply that was not vulnerable to foreign control. A resource that had once been invisible now stood at the center of strategic planning. And the effects rippled outward. Military operations accelerated. Logistics planners could commit vehicles without fear of attrition from wear alone. Aircraft maintenance improved. Operational tempo increased across multiple theaters. The rubber crisis did not win battles directly, but it removed a constraint that could have lost the war quietly. The significance of that achievement was not fully appreciated at the time. There were no parades for chemical engineers, no medals for plant operators. But inside factories and depots, one truth was clear. The war machine was moving again. Not because the enemy had weakened, but because an invisible bottleneck had been broken. And only later would it become apparent that the most important consequences of this program had little to do with the war itself. They were just beginning. When the rubber crisis ended, most people assumed the story was over. Natural rubber plantations in Southeast Asia would reopen. Shipping routes would recover. Prices would fall. Synthetic rubber, many believed, would quietly disappear. It had been a wartime necessity, nothing more. That assumption turned out to be wrong. What the United States had built under pressure was not a temporary substitute. It was a fundamentally different system. By the end of the war, America was producing more synthetic rubber each year than the entire world had produced in natural rubber before 1940. The plants didn't shut down, they expanded. And once the urgency faded, engineers began to do what they had never had time to do during the crisis: refine. Processes became cleaner, control systems improved, material properties were tuned with precision. Synthetic rubber revealed an advantage that natural rubber could never match. It could be engineered. Instead of accepting whatever properties a tree produced, manufacturers could design rubber for specific purposes: harder compounds for heavy trucks, flexible blends for aircraft, durable formulations for industrial machinery. What began as a desperate workaround became a superior material. By the early 1950s, synthetic rubber captured the majority of the American market. By the 1960s, it dominated globally. Today, nearly 70% of all rubber products worldwide are synthetic. The original natural rubber supply chain never fully recovered its central role, but the deeper legacy of the program went far beyond rubber itself. The synthetic rubber effort pioneered a new way of building industry: standardized plant designs, modular construction, parallel development instead of sequential planning. These methods spread rapidly. Aircraft factories, shipyards, ammunition plants. The idea that massive industrial systems had to be built slowly, cautiously, was quietly abandoned. Speed became a strategic asset. So did collaboration. The forced sharing of patents and research data between competing companies demonstrated something uncomfortable for peacetime economics. That innovation accelerated when information flowed freely. After the war, this lesson influenced government-funded research programs, industrial standards, and large-scale infrastructure projects. The workforce trained during the rubber program carried its knowledge elsewhere. Hundreds of thousands of workers gained experience operating large chemical plants. They became the backbone of America's post-war chemical and materials industries. Plastics, synthetic fibers, industrial chemicals, pharmaceuticals. Entire sectors trace their roots back to techniques refined under rubber shortages. And then there is the lesson that remains relevant today. The synthetic rubber program did not succeed because engineers found perfect solutions. It succeeded because they refused to wait for them. They worked with flawed materials, inexperienced labor, incomplete information. When reactors overheated, they didn't redesign the entire system, they improved cooling. When steel ran out, they used concrete and wood. When labor was scarce, they trained faster. Progress came not from brilliance in isolation, but from relentless. This mindset echoes in modern challenges: semiconductor shortages, energy infrastructure, supply chain resilience. The details differ, but the structure is familiar. Critical materials concentrated in a few regions, long construction timelines, complex manufacturing processes. The lesson of 1942 is not that problems like these are easy. It is that they are solvable, if systems are designed for speed, cooperation, and tolerance for imperfection. In 1942, the United States did not defeat a rubber shortage with a single invention. It defeated it by building an entire system, fast enough to matter. The war was very much for the next bandem from the warm as well, including the part of the transpation is entire fast. But it could have been lost without it, and that is the uncomfortable truth behind many moments of history. Victory often depends not on the things we celebrate,